Any questions on the homework problems? Great, pretty good job on number 29. I told you that was the one I was really going to look at as I come around here drawing pictures and trying to do that area part of it. Kind of like the long way of doing the derivative with the definition alphabet. This is not the definition of area necessarily. I mean, the definition of, we'll get into a formal definition of an integral later. But this is showing a connection to antiderivative, which is, of course, what the fundamental theorem part 1 says. Okay, this basically says that if you had to summarize in words what this is saying, all this symbols, this is saying that, put it in quotes, because it's saying this. It's saying that this thing is the antiderivative of little f. That's what the fundamental theorem part 1 is saying, right? That's what this sentence is saying. Now it seems strange because it's got a derivative in it. It's got d over dx. It's got derivative. Well, that's how we show something's an antiderivative. We show something's an antiderivative of little f because when we do the derivative of it, it gives us back little f, right? X, 1/2 x squared is the antiderivative of x because when we do the derivative of 1/2 x squared, we get x, right? Sine is the wait, I did that backwards. Yes, sine is the antiderivative of cosine, right? No. The derivative of sine is cosine. Yes. So the antiderivative of cosine, that's what it meant. The antiderivative of cosine is sine, right? Because the derivative of sine is cosine, right? The antiderivative of cosine is sine because the derivative of sine is cosine. The antiderivative of x is 1/2 x squared because the derivative of 1/2 x squared is x, okay? So this is the antiderivative of little f because when you do the derivative of this, you get little f, okay? So that's what this is saying, all right? So even though it's got derivative in it, what this is really what this is really getting at is telling us that this thing called the area function, this thing with an integral symbol and an x up here, this is the antiderivative of little f. So let me pull up, I don't remember if I gave you guys this handout, and if I didn't, let's just do it right now. Let's see, I can't remember which one. No, it's not that much. No, I did give you this. 2014, you guys have this little packet, the 2014 free response questions. Yeah, pull that out. And go to number 3. Okay, now, this is not that problem. This is from the 2017 test right here. Okay, this is from last year's AP test. Now, look what they give you. They give you an F prime graph. It's got lines and half circles. I mean, stuff we did right back at the beginning of the year, right? So you could, that's not it, right? Yeah, this is different, right? You guys have 2014. This is 2017. I'll get to 2014 in a second. But notice what they do. They give you the graph of F prime. Well, again, this goes right back to chapter 1, and they're going to ask you a bunch of chart stuff. And there's going to be some, actually, I'm not sure they have, they don't have any areas in there, but they ask it in a little bit different way. It says you have to actually think of it as being areas. So we'll come back to this in a second, but they tell you this is F prime, and they tell you that F of -2 equals 7. So find the values of F of -6 and F of 5. Okay, so we'll get to this, that part of it here in a second. But if we look at the one in 2014, or we may come back, I may assign that and have you look at that actually another day. If you look at this one, they tell you this is the graph of little f. Again, with lines, and so we'd be able to do areas and stuff. And then look at how they define the g function, okay, right here. This is very, very common on the AP test. Well, what are they telling you right there? That g is what? They're telling you that g is the antiderivative of little f. Okay, so this is where this fundamental theorem part 1 comes into play right here. They're telling you that g is the, now it's not big G, right? A lot of times we use a capital letter to be that, but that's not what we do. Now, all of the questions, if you go through the questions, do you notice how they almost all are about g? All the questions are about g, but yet they give you this graph of f. Okay? You cannot use f to answer questions of g, about g, unless you've made some connection to what g is compared to f. So what you'd want to do right here on this problem is you'd want to write this. We're going to talk a lot about that as we go through the year, and hopefully by the time we get towards the end of the year, that'll be automatic for you. As soon as you see this, you'll write this. Well, isn't that exactly what we just showed on the fundamental theorem part 1? It's exactly what we just showed. We said the derivative of the area function, right? Fundamental theorem part 1 that I just had up there said the derivative of the area function, right? And g is the area function. So the derivative of the area function is equal to the thing inside little f. And when you make that connection, now you can start talking about all the chart stuff. So when it says find g of 3, well, g of 3 is easy. G of 3 just means what? The area from -3 to 3. So here's -3, here's 3. So what do we want? We want that area, and then we're going to have a little triangle here. Now we can figure out this slope. This goes down what? 1, 2, 3, 4, goes down 8 over 4. So that's a -2 slope. So if we go over 1, that's going to go down 2 right there. So we can tell that area is going to be -1. And then this is 1, 2, 3, 4, 5 across, and 4 up. So this would be what? 5 times 4 is 20. This would be 10. So 10 and -1, this would be 9, I think, if I did that. Did I do that right? That makes sense? This would be 1 across here and down 2, because we can tell this slope is -2 here. Okay? So find g of 3. So you can see this fits right in with what we're doing right now. Now, where is g both increasing and concave down? Well, see, this is just a chart question, isn't it? Because we've now made this connection with g prime. So what we have here is g, g prime, g double prime. If we think of the chart, that's the same as f. And this would be the same as f prime, right? If I'm thinking about the chart, since g prime. So on my paper somewhere, I want to have this connection. So where is g increasing? G's increasing when this is positive, meaning when f is positive, right? When g is increasing when g prime is positive, but we said right here that g prime is f, right? That's what they told us right here. So where is this positive? Well, from, let's see, what they want, -5 to 4, so that's all the way across here. So all the way from -5 to 2, right? Now that's when it's increasing. Now when's it concave down? When is this graph concave down? When this graph is, remember the chart? Decreasing. G is concave down when this is decreasing, which would be when G prime or F is decreasing. So this is decreasing from -5 to -3, and it's decreasing from 0 to 2. So -5 to -3, and from 0 to 2, which would be when this is both positive and decreasing. And then you give a reason for your answer. This is when G prime, and then a lot of times I would put in parentheses, or F, but since I've made this connection right here, that G prime is equal to F, since I've written that on my paper, I can talk about G prime and know I'm talking about the graph of F. So when G prime is both positive and decreasing is when G is increasing and concave down. Okay, and that would be my rationale. But again, it's really just a chart question. Okay, and then they say, okay, H is defined by G over 5x. Well, find H prime of 3. Well, before you can find H prime of 3, you got to find what? H prime of, before you can find H prime of 3, you've got to find H prime of x, right? You got to find H prime of x, and then you can plug in a 3. So we need a quotient rule. So derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom all over the bottom square. Right? Now you can plug a 3 in there. Okay? Now you can plug a 3 into there. Well, what's G prime of 3? What's G prime of 3? How are you going to get G prime of 3? That's F of 3, right? G prime of 3 is F of 3, because G prime and F are the same thing. G prime of 3 is F of 3. So you just go up to the F graph, go to 3. We already said that was -2, right? Over 1 down 2, because the slope is 2. So that's -2. We know that that point right there is -2 because of the slope of that line. Okay, so that'd be -2. 5 times 3 would be 15. G of 3 we already found. That was 9. We found that earlier, right? And then 15 squared, right? So you got all that you can find. Okay? All right, and then going down to the bottom, the function P is defined by F of this. Find the slope of the tangent line to P at the point where x is -1. What's that mean? Find the slope of the tangent line. Come on. The derivative, yeah, right? Derivative is the slope of the tangent line, right? Derivative. So all they're saying is find the derivative. Just another way of saying find the derivative. Oh, how do we do the derivative of P? How would you do the derivative? What would I write? F prime, what do I do with the inside? Leave it alone, times 2x minus 1, right? That's P prime of x right there. So the last two questions are just some derivative practice, right? A quotient rule, a chain rule, and now we plug a -1 in there. But again, well, F prime, yeah, okay, that's good. That's about F. This one isn't about G. F prime is going to be the slopes of this graph up here, right? So we put a -1 in here. That'd be 1 minus -1. That'd be 2. That'd be F prime of 2. And put a -1 there. -2 minus 1, that'd be -3. So F prime of 2, you can just go up there and get the slope, right? F prime would be the slope off that graph. So go to -2, get the slope, and throw it on. Okay? But I want you to see that. I just want you to see a problem in context of what we've been talking about here with this area function. Very, very common that they do that. Okay? Very, very common that they do that. All right? And then just to give you a little hint on this one, we'll come back to this one another time. But this is going to involve area too, because this is the F prime graph, and they're saying F of -2 is 7. So that means if you think of an area function, right, that you were starting somewhere and you went over here to -2, you got an area of 7. But if you keep going, so if they want f of -6 or f of 5, if you keep going, you're going to keep adding on areas. That's what f's going to be. That's the antiderivative of this graph. It's going to be the area. It's basically the area function. Okay, but that one's a little trickier the way they worded it. But then on what intervals is f increasing? Of course, the rest of this is just chart kind of stuff. Okay, but that's how areas will get evolved. Since we now know that area is antiderivative, a lot of you would look at this problem if before this week or last week, we look at a problem like this, say, well, this is the f prime graph. And they tell us this is the f graph, fine, but how are we going to find those values on the original if we can't do an antiderivative, right? We don't have an equation. Well, we now know areas. Areas will give us those values. Okay, so we'll be doing some more of that. All right. So here's just to reiterate a couple things. Here's just an example. I don't. Was this a homework? I can't remember if I put this on here. I don't think it is. 12 through 14 was just more of that other question. Yeah. Okay. This is just, I just wanted to, again, give you an example graphically of how that left endpoint is just a vertical shift. Okay, so let's say and how the same F graph produces multiple antiderivative graphs, which of course we've always known, and that's the plus C, and we've said, okay, if I start with a little F graph and want to draw its antiderivative, its area graph, we wouldn't know where to start, except we learned last week we get a free initial condition. What's the free initial condition on this one? If this is called big F, what's our free initial condition? Big F of 0 is 0. We know that if we put a 0 into here, we get an area of 0. So what that means is that tells me that the big F graph has to start right there. So then if we look at this, and now let's think slopes. Okay, let's think slopes first, then we'll think areas. So we would say, okay, these are negative values right here. These are negative and getting less negative towards 0. What's this doing? Going down but leveling off, right? Then these values turn positive and get more positive. So that graph's going to go up, up, up. Okay, if we're thinking slopes. Let's go back this way. These are negative and getting, slopes work better to go left to right. Okay, slopes work better to go left to right. So we come this way. We got positive and getting less positive. So positive slopes and getting less positive. And then negative and getting more negative until there. Right? So we can see why that graph looks like it looks. Now let's look at area. So the area is from 0 to x. So what kind of area are we picking up as we go this way? What kind of area is this? Negative area. Picking up negative. What are the chunks? What kind of chunks am I picking up as I go this way? Smaller and smaller chunks, right? If I was sliding that, think of that orange. If I was sliding that, I'd be picking up smaller and smaller chunks of negative. So what happened? Area graph's going down, but it's leveling off because I'm picking up smaller chunks. Okay? Then we go this way, start picking up positive area, bigger and bigger chunks, so that area starts going back up and going up faster because I'm picking up bigger chunks. Now, you got to think of this there's a couple different ways we can think of this. If we think of sliding, remember I'm thinking of sliding now, I'm thinking of sliding that X, okay, back to the left. So here's my 0 point, here's where I have no area. So as I start sliding this way, I'm starting to pick up some area, right? What kind of area is that now? That's positive area because I'm going backwards, right? But I'm picking up smaller and smaller chunks of positive area. So as I go back this way, sure enough, my area graph's going up, but leveling off. Then I go this way, I start picking up some negative, bigger and bigger chunks of negative. So down, 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 right? So that's one way to think about it because it makes sense. It kind of makes sense. When you're thinking of area, you're thinking of sliding it, it makes sense to start at this 0. It makes sense to start here and slide that way, and then come back to here and slide that way. That makes sense. But here's the thing about that. It doesn't matter. It doesn't really matter where the left endpoint is. The only difference is going to be that orange area, whether you're losing negative or gaining positive. Aren't those the same thing? Isn't losing negative area the same as gaining? So again, visualize this now. So I got my slider right here. There's no area shown. Now I grab it and I drag it way over here, right? So what do I now have? I have a bunch of orange area here, right? I got a bunch of orange area. I've now slid that thing over to here, right? Everybody with me? Now let's go left to right, because chart stuff always works better going left to right anyway, right? Increasing, decreasing, stuff like that. So now, what is this area right here? Positive or negative? Remember, my left endpoint is still 0. So I grabbed that slider, I went this way, filled up this area. It's still 0 to x. So what's this area? This is negative area right here, right? This is negative area because my left endpoint is x, okay, or is 0. Okay, so this is negative area. So as I slide this, what's happening to the orange? It's going away, isn't it? I'm losing it, right? Remember, I grabbed that slider, I went this way, I got a bunch of orange here. So as I go this way, it's going away, right? So I'm losing what? Negative area, right? I'm losing negative area, which means a gain of area, right? Losing negative means a gain. So what's happened? This is going up. See what I mean? Now, what if the left endpoint wasn't 0? What if the left endpoint was over here at negative 10? Well, now when I grab that slider and come over to here, is this filled in orange right now? If my left edge is over here at negative 10, is any of this orange filled in? No. So now as I slide this way, I'm picking up area, right? And what kind of area is this now that I'm going the right direction? Positive. So as I come this way, now I'm picking up positive area. Does that make sense? So the area graph's going up. What I'm trying to get you to see there is the reason the chart questions, the left edge doesn't matter. The reason we know it doesn't matter because it's a vertical shift, right? We know the left edge is vertical shift. But as far as an area thing, you got to understand that the sliding back and forth doesn't really matter if we start here and go this way or if we go this left to right. The only difference when you change that left endpoint is either the orange will already be there and you're losing negative, or the orange isn't there and you're gaining positive. But those are the same thing, right? Losing negative or gaining positive are the same thing. Okay, so as far as the chart, what's happening to the chart doesn't matter. Okay, so we change our left endpoint to 2. We change our left endpoint to 2. What's our free initial condition? G of 2 is 0. So that means that's the point we know. And then we could go through all those same things, right? I could grab my slider right here. 2 to 2 would be 0. Drag this way, I'd pick up some positive area. There it goes. Come back this way, I'd be picking up positive area this way too, right? Because I'm going backwards now, right? This is my starting of my slider. So I'm picking up positive area. Sure enough, going up, up, up. Then I pick up even more positive area, but it's littler chunks, right? Then I start picking up this negative area, right? So it goes down, right? Or I could bring my slider way over here. This is all filled with orange. This is all backwards. And then I could say, okay, I'm losing negative area, so that makes it go up. Then here I start losing this positive area, makes it go down. And then finally I get back to my starting point. Then I start picking up positive area. And there it goes. Okay, no matter what, you still get this same picture. It's just shifted now. It's just shifted. Okay, this one went through 0, 0. This one goes through 2, 0. Okay. So I know I'm saying a lot of the same things over and over again, just in different ways, but that's the key to this, right? I mean, that's the overall concept I want you to get with and get comfortable with this notation here. Okay. All right. Let's see. That was from another day's homework. Okay. So here was some of 29. Looks like you guys did a pretty good job of that, so I'm not going to get too hung up on going through that. I think on Wednesday's quiz, you're probably not going, partly because it's a shorter day. We have 60 minutes, so I'm not going to have you go through all the, like a trapezoid thing like that. We're going to go ahead and use our free initial condition, use our antiderivative business here to get it. So if I give you a problem like this one, okay, so if I give you this right here, let's just do that. Let's go through that. I don't think any of you did it necessarily, but let's go and let's just take this problem right here, okay? And let's say I gave you this problem, and let's call it G, okay? and I said find a formula for G. Okay? So, one way to do it would be what I had you do today. Draw a picture, get the area, go through it. We don't have to do that. Okay, we did it. It's pretty cool. Here's a trapezoid. It came out an antiderivative. Wow, unbelievable. Where'd that come from? Okay, but now we're just going to use that fact. Okay, it's an antiderivative. So, what do? We just take this thing and we do the antiderivative. What's the antiderivative of 2? Be careful now. 2 what? This is the part we're still not confident on, are we? We know it's one of them. It's either T or X. Which one is it? It's X. When it's in here, it's got to be a T. If there's an X up here and it's in here, it's got to be a T or something other than X. When it comes out of that, it's always an X. Okay? It's always whatever this is. Right here. I mean, I could really mess with your heads and give you one of the tests where I put all the X's in here and make that a T up there. Okay? Probably not going to do that to you, but it's the same idea. If the T's up here, that's the key, and this would be a T over here. And then you'd say, okay, when it's in here, it's got to be X. When it comes out, it's got to be T. Okay? Just be backwards. Okay? And it could be that way, but I'm not going to do that to you. All right, so anyway, antiderivative 2X. So big G of X would be 2X minus 3/2 X squared plus C. Right? It's some antiderivative. So it's plus C. It's called the general antiderivative. But we know enough that we can find that C. What do we know? We know G of 1 is 0. We know G of 1 is 0. So we put a 1 in for X, both places, and we solve for C. So we get 2 minus 3/2 plus C is equal to 0. 2 minus 3/2 is 1/2. Plus C equals 0, so C equals -1/2. Now put that back in. So my final answer, G of X, is 2X minus 3/2 X squared. And I don't care what order. Usually we'd write the X squared first, and the C is -1/2. So you know G of 1 is 0, so you put a 1 in for X, get a 0 out. What does C have to be? So we can do that, and so you don't have to go through the whole trapezoid and all that area stuff you did, because we now have this free initial condition that we can find the C for. Okay, so anytime I'm given this, if we can do that antiderivative, we can do it, right? Now, some of these things don't have antiderivatives, right? And we'll be talking about that. That's one of our things we'll be getting into here later. What do you do if the thing doesn't have an antiderivative? Because there are functions that don't. Okay. All right. Was this part of the homework? No? Okay. Oh, yeah. Right. Because I think it says on the thing, this sheet, we're doing it in class. Okay, so let's take a look at this one. So now let's know. Because I just got to tell you, you're not going to have to do this. Right? Because that'd be error. See, because this one doesn't really have an antiderivative. Now it does. What you'd have to do on this one, if you wanted to do an antiderivative, this is a piecewise. So you would have to, this would be y equals 2 minus x, and this would be y equals 2 plus x, right? It'd be a y-intercept of 2, it'd be a positive 1 slope. This would be a negative 1 slope. So what you'd have to do is you'd have to do 2 separate pieces. Okay, so on this side you'd have 2x plus 1/2 x squared plus c, and here you'd have 2x minus 1/2 x squared plus c. Okay, and you would just have, that's how you do your antiderivative, because there is no antiderivative of absolute value. So you just break it up into its 2 pieces. Okay, but we can do that as an area too. All right, so let's not do that. All right, let's move on to this. This is the big deal for today. So part of your homework, you're going to have 61 through 65. Okay, so I'm going to do one with you right now that's a lot like 61 through 65. Now, the whole point of doing 61 through 65 is to come up with the other part of the fundamental theorem. We're going to actually come up with it together, but I still want you to do 61 through 65 because it's a good review of the splitting apart rule that we had with integrals back at the beginning of this chapter. okay, which is something you need for Wednesday's quiz also, okay? But this is going to give us part 2 of the fundamental theorem, which is what we're really after, because this is the question that we really care about right now. I mean, obviously fundamental theorem's really cool, and the connection, I mean, my God, without all that stuff, there is no calculus, and it's not that big a deal, that whole connection. But as far as usefulness of what we'd like to be able to do, we would really like to be able to look at a parabola from -3 over here to 4 and be able to get that exact piece of area right there. That would be great to be able to do, okay, and not need geometric shapes. Now, we have a hunch that antiderivatives are involved, right? And we can type in our calculator and just get that answer, but we have a hunch that antiderivatives are somehow involved. How are they involved? Okay, so let's say I had this area function. I just defined big F to be this. So I got my parabola, but I got to use a t when it's in here, right? So I got t squared. And I'm defining big F to be that. And I'm looking for this. Okay? Well, it dawns on me that I've got that thing about splitting up areas. That the integral from -3, because this is my little f right in here, right? This is little f of t. This is, now notice now wait a minute, time out. Is it okay to have x in here? Why? Because there's not an x up here, right? What does this represent right here? We're going to talk about this more tomorrow and then after the quiz a lot. What's the difference between this integral and this integral? They both represent what? 4 letters, starts with an A. Area. Right? They both represent area. Okay? But what's the difference? This is a specific fixed piece of area. So in the future, when I ask you this question, what does this definite integral represent? The good answer is a number, a constant, right? This is a number. It's a fixed piece of area under the x squared graph from -3 to 4. It's just a number. What does this represent? A function, a whole bunch of areas. The area from -1 to 2, -1 to 3, -1 to 4, it's a whole bunch of areas. It's a function. It's an area function. It's a specific one because it's got a certain left endpoint. It's got a free initial condition, so we can find the plus c. But it's the antiderivative of x squared is what it is. So it's a function. So it's very important to understand. Yes, these both represent area. These both represent area. But this one represents a fixed piece of area, a number. This represents a function, a whole bunch of areas at various right endpoints. Big difference between those two. But we're looking for this. Okay, so it dawns on me that my area from -3 to -1, so we're okay using x in here, right? Because we don't have an x up here, we can use anything we want in here in a definite integral, not a problem, right? Only in that one, when the x is up here, we got to use something else. Okay, so it dawns on me that the area from -3 to -1 plus the area from -1 to 4. Now remember, the -1 doesn't have to be in between there, but remember that rule we had? Isn't that the same as the area from -3 to 4? Isn't that true? Okay. Now, it also dawns on me that if I would flip these two around, right? I could rewrite this as the area from -1 to -3, but then the answer would be opposite, right? Might be negative, might be positive, depends what the original is, but it's opposite, right? So if I switch these two numbers around, and some of you were wondering early on, what would ever be the advantage of flipping those around? Well, I think you're going to see it right now. Okay, now, go as I didn't leave myself. All right, does that make everybody okay with that so far? Okay, so that should be equal to this original area here, though that should be the same.
Now it also dawns on me since why did I use -1? Because I had -1 here in this function called big F, so I wanted to get a -1 involved here somehow. So what I did is I just stuck it there and there because I knew that rule I had. Okay, now another name for this is negative big F of -3, isn't it? This is the area from -1 to -3. Well, big F is the area from -1 to x. So if I put a -3 right there, that's like putting a -3 right there. Would you agree with that? Okay? And then this one's already, I don't have to mess with this. Another name for this would be what? Big F of 4. And it seems, and that should be equal to that right there. So let's rewrite that over here. So what it seems like I'm saying is the area of this should be equal to big F of 4 minus big F of -3. Are you with me? Okay, now how can I get big F? Now, and the problem you might say would be, well, okay, that didn't help you much. Big F of 4 is just the area from -1 to 4, and the whole point is we don't know what those areas are. Oh, wait, though. We do know that big F is what? What did we just learn? It's antiderivative, right? I mean, what did we learn back here? Find a formula for G, right? We can do, and we got this free initial condition, we can find a formula for G. So here we can find a formula for big F, can't we? Okay, so what's the antiderivative of x squared? So big F is going to be 1/3 x cubed plus some c. But what do we know? We know that big F of -1 is 0, right? We know that big F of -1 is 0, right? You go -1 to -1, that's going to be 0. So let's put that in. So 1/3 -1 cubed plus c's got to equal 0. So 0 equals -1/3 plus c. So c is equal to 1/3, right? So my big F function is actually just 1/3. Now, you might be thinking, geez, we got to go through and find that c every time. Well, watch this. Turns out the answer is no, because look what I can do now. So big F of 4, okay, great. I just found big F of x right here. So that's cool. So now I can just do big F of 4. So I can go 1/3 times 4 cubed plus 1/3, and then minus, and then now I put in a -3, so it'll be 1/3 times negative. Why do I always squeeze myself? All right, and 1/3 -3 cubed plus 1/3, right? Now, when I look at that, I think, did I really need to find that c? Did I even need to find that 1/3? Because what's going to happen? It's just going to subtract out. I'm going to have a plus c on this one, and I'm going to have a plus c on that one, and when I subtract them, the c is going to go away. So now it turns out I don't even have to worry about this -1. I don't even have to worry about doing any of that plus c business for that. All I really need to do is just take the normal antiderivative without the plus c, stick in a 4, stick in a -3, and what is that, 64/3? This would be -27/3, which would be -9, so this would be +9. Well, I better leave it 27/3. Add those together, what is that, 90? Did I do that right? 91/3, 30 1/3. Try it on your calculator. Do this interval right here. Do this interval. See if that's that'll come out. So you can get lost a little bit in the notation, but that seems to be a pretty big deal. We thought finding the area was going to involve the antiderivative somehow because of all the work we've done over the last several days. Using the area function and our rules about splitting apart, we took this definite integral, which we know is just a fixed piece of area, and we said, okay, let's rewrite it in the language of this big F, which I still want you to do on 61 through 65 to get the hang of this. It's going to look very much the same. So whatever your left edge is, that's what you want to split it apart. Put that number there. You flip one of them, and so now you got the -1 down here as the left edge, which is supposed to be for big F. And so then whatever number's up here is your big F. That's big F of -3. That's big F of 4. And so there you go. It looks like, so the real exciting part of this then, the real useful part of this is, okay, it looks like if we're wanting to do an area, all we have to do is the antiderivative of that guy, forget the plus C because it'll subtract away anyway, do the antiderivative, stick in a 4, stick in a -3 in that order, subtract them, and we got it. And it turns out that does it. And that is called then Fundamental Theorem Part 2. FTC, Fundamental Theorem of Calculus. FTC, Fundamental Theorem of Calculus, Part 2. And this is the really useful part of the fundamental theorem, or of the fundamental theorem. And notice, since we're doing a fixed piece of area, this is a definite integral, right? When we have that x up there in the top part of the integral, that's not a definite integral. That's a function. That's an area function, so that's different. A definite integral is a definite piece of area. Just remember that. When we talk about definite integral, we're talking about the integral from A to B. We're talking about a fixed piece of area. We're talking about a number. Just like f prime of 2 is a number. It's the slope at 2. Okay, this is a fixed piece of area. So we can go ahead and put the x's inside. That's fine. So what do? We do the antiderivative. Any old antiderivative, just leave off the plus c. Doesn't matter, because it would just subtract away anyway. Put in a b, put in an a. Now, here's how we want those problems to look when you actually do it. So let's maybe underneath your fundamental theorem part 2, let's redo that one. Let me show you what this would look like, because that's really messy. Okay, here's what one would actually look like. Okay, so on your part of your homework, I'm not sure a lot of your homework, some of your homework there's going to be there where they just tell you to find the area. Okay, so here's what it would look like. So you would say, okay, do the antiderivative, 1/3 x cubed. We call this right bracket notation. Okay, so this is how I want you to write this when you're doing these problems. Okay, if I give you 7, I just say use the fundamental theorem part 2, or if it just says evaluate the integral. From now on, if it says evaluate the definite integral, this is what we'll use. If it says evaluate the definite integral, this is what we'll use. Okay, if it doesn't tell you to do something differently. Okay, so we'll do our antiderivative, we'll right bracket it, we'll put our -3 here, we'll put our 4 here. We don't want the integral symbol anymore because we've already done the antiderivative. So that goes away, the integral symbol goes away, and we use this right bracket, and then we're going to plug in our 4, and then we're going to plug in our -3. Now parentheses become really important here, not so much in this problem, but in one where the antiderivative was multiple terms. You got to be careful. And of course, then we get our 64/3 plus our 27/3. We get our 91/3. Okay. Now this would be in a no calculator situation, obviously. If it's a calculator situation, you're just going to type this in, right? And later on, that'll happen. We'll set up integrals. We'll go to our calculator, just get the answer. But for now, it's going to be your questions like this will be in the no calculator part, probably. Or to be honest, because sometimes the fractions might get a little messy. So I haven't decided. I'll let you know tomorrow. The quiz, I might let you have the calculator. If I do, it'll just say use fundamental theorem part 2, and I want you to show your work. Now, I want you to write that out, and then if you go to your calculator from there, you can go to your calculator. Okay? But it's possible the whole quiz might be no calculator, because quite honestly, we haven't hardly done anything with the calculator here in chapter 5. So the whole thing might be.
Right bracket, you just plug in -3 and 4.
But you start with the 4 first.
So that's all.
That's it. That's it. But you do the antiderivative, do your right bracket to put your two numbers on, and then do that. But I want you to write that much of it out. And that's what they're looking for in the AP test. When, right, they'll say use the fundamental theorems. They won't say part two always, because actually some books reverse it. When I learned it in high school, this was fundamental theorem part one, actually. Because it's the most useful, as far as doing problems, okay? I think books nowadays tend to reverse them. I think conceptually, theoretically, the other one's more important. But as far as what you use every day, it would be more this one, okay? So a lot of times AP tests, they don't call it part one or part two. They just might say, use a fundamental theorem to evaluate this integral. Well, they're talking about this one, okay? We're talking about this one. All right, so go ahead and work a little bit, a few here in 5.2. So 5.3 then is where we've now learned about this, but there's still going to be some chart stuff. So when you get into 5.3, there's going to be some chart stuff for sure. I mean, but gosh, that part should be easy. So on the quiz on Wednesday, I mean, I give you a big F area function and then ask you questions about it, just chart stuff. So a bunch of this stuff in 5.3 is chart stuff. When you get to 19 through 30, that's the part where you're using the fundamental theorem, the right bracket. So 19 through 30 is when you're using FTC part two, kind of the new thing for today. Okay. The rest of it's, kind of good review for things you've already done. All right.